Welcome to the Hacker Strategy Session. I am your host, your resident Cambridge expert, and today we are going to find the back door into every complex mathematical investigation the examiners try to throw at you. We are focusing specifically on the Cambridge Mathematics 0580 syllabus, and we're looking at those high-mark logic-bending investigation questions that separate the top-tier students from the rest of the pack. Now, imagine sitting in that exam hall. The clock is ticking down. The tension-building music in your head is getting louder. I see two types of students every single year. First, there's Alex. Alex tries to memorize everything. He overloads his answers with raw mathematical facts, but he shows absolutely zero analysis. He hits a wall the second a question looks unfamiliar. Then, there's Sam. Sam is quick, but Sam rushes. Sam completely misses the specific command word requirements the examiner is begging for, losing easy method marks left and right. Today we are going to fix both of those approaches. We are stepping into the shoes of the inductive detective to decode these investigations using our ultimate mathematical success blueprint. We are going to work smarter, not harder.
So let's start with a classic Cambridge-style challenge. I want you to really visualize this. You have a massive 10 by 10 by 10 cube. You dip the entire thing into a bucket of bright red paint, so the entire outside is covered. Now you take a saw and slice it up into 1,000 tiny 1 by 1 by 1 cubes. Here is the question the examiner drops on your desk for a massive chunk of marks. Exactly how many of those smaller inner cubes have zero painted faces? Just sitting there, perfectly clean, completely hidden on the inside. Now, Alex would sit there trying to literally draw out 1,000 cubes, wasting 20 minutes of the exam and ultimately giving up. Sam would just guess a random volume formula, miss the command words, and get a big red cross on the page. But you, by the end of this session, you are going to see exactly how to systematically break this down without a single formula memorized beforehand.
To get there, we need a strategy. Here is our agenda for today's session, which is essentially your roadmap to securing top marks. First, we'll dissect the painted cube puzzle, showing you how to organize raw data. Second, we'll move to formulating the cube rule, where we turn those specifics into algebra. Third, we'll tackle the triangle counting challenge, to show you how this applies to two-dimensional geometry. Fourth, generalizing the triangle pattern. And finally, number 5, we're going to apply this logic to visualizing vector mathematics, which is a notorious area for lost marks in the 0580 syllabus. Let's get into it.
Step 1, the painted cube puzzle. Here is where we start breaking down three-dimensional geometry into clean, scorable categories. When you see an investigation question like this, the examiner's primary assessment objective is checking your ability to categorize and simplify. You need to use what we call the PEEL framework: point, evidence, explanation, and link. The very first point you need to make to the examiner is that a complex shape is just a combination of simpler parts. To simplify this 3D object, you absolutely must define your categories. Don't do this in your head. Put it on the paper. Let's imagine a basic 3 by 3 by 3 painted cube first. When we break it apart, the tiny blocks aren't uniform. We categorize them. Type A cubes are the corners. Because they stick out on 3 sides, they have exactly 3 painted faces. Type B cubes sit along the straight edges between the corners, meaning they only have 2 painted faces exposed. Type C cubes are sitting right in the middle of a face, so they only get 1 painted face. And finally, type D cubes. These are the elusive ones, completely buried inside, with 0 painted faces. Defining these 4 categories clearly on your exam paper shows the examiner you understand the structure. This is your foundation. Now we provide our evidence for the PEEL framework. Let's apply those categories to that standard 3 by 3 by 3 cube, which has 27 small cubes in total. Look at the corners. A cube always has 8 corners, right? So naturally there are 8 type A cubes. Now look at the edges. A cube has 12 edges, and on a 3 by 3 by 3 cube, there is exactly 1 type B cube sitting in the middle of each edge. So that's 12 type B cubes. A cube has 6 faces, with 1 type C cube dead center on each face, giving us 6. And if you peel all that outer, painted layer away, you are left with just a single, unpainted type D cube right in the dead center. 8, 12, 6, and 1. These are our baseline data points. Now, before we continue and scale this up to secure those high-level marks, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's keep hacking this problem. We are moving into phase 2, formulating the cube rule. This is where we transition from specific, concrete numbers into generalized algebra. This is where the command word changes from calculate to investigate or show that. Top Cambridge students know that a table is a goldmine for marks. When you are given a pattern, map it out. We start with our 3 by 3 by 3 row, 8, 12, 6, 1. But the examiner wants to see if we can scale it. If we expand it to a 4 by 4 by 4 cube, let's look at the numbers. The corners, type A, remain exactly 8. A cube always has 8 corners. The edges get longer, so type B jumps to 24. The faces get wider, so type C jumps to 24, and the hidden inside volume grows, giving us 8 type D cubes. And if we look at the bottom row, scaling all the way up to our starting hook question, a 10 by 10 by 10 cube gives us exactly 512 completely unpainted inner cubes. Look at Alex. Alex is still trying to manually count these on his paper. Sam rushed and just cubed the number 10 and wrote 1,000. Both lost the marks. So how did we get 512 so quickly? Let's decode the explanation part of our PL framework.
We found the backdoor using inductive reasoning. We turned the pattern into an algebraic rule for an n by n by n cubed. Here is the secret. You just strip away the outer 2 layers to find the core. Type A corners are a constant 8, easy mark. For the edges, type B, there are 12 edges on a cube, and the number of edge pieces is the total length, n, minus the 2 corner pieces on each end. So the formula is 12 times n minus 2. For the faces, type C, there are 6 faces, and the area of each face's unpainted center is an n minus 2 by n minus 2 square. So 6 times n minus 2 squared. And for the hidden inside volume, type D, it is literally just a smaller inner cube with dimensions n minus 2 cubed. So let's link it back to our 10 by 10 by 10 problem. 10 minus 2 is 8. 8 cubed is 512. We just turned a massive geometrical nightmare into a 30-second arithmetic problem. That is how you guarantee top marks. Now, what if the examiner throws a massive curveball? What if it's not a perfect cube, but an irregular cuboid with a distinct length, width, and height? Your logic holds up perfectly. The corners are still 8, but now your 12 edges are split into groups of 4 lengths, 4 widths, and 4 heights. Your 6 faces are split into 3 matching opposite pairs, and your inside, type D, isn't a perfect cube anymore. It's an inner cuboid, calculated by multiplying length minus 2 times width minus 2 times height minus 2. It looks intimidating, but because we built our foundational understanding, we can hack any variation they give us. All right, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's transition to our interactive workshop. We are moving from 3D cubes to 2D sequences with the triangle counting challenge. I'm giving you 60 seconds on the clock in your head for challenge 1, the data scan. Look at this visual sequence. Imagine an isosceles triangle with one straight vertical line drawn right down the middle from the apex to the base. With 0 horizontal lines crossing it, you can count exactly 3 triangles, the large main one and the 2 smaller ones inside it. Now draw one horizontal line straight across the middle. You've just created a smaller copy of the whole shape on top. Now there are 6 triangles. Add a second horizontal line, and the sequence hits 9 triangles. 3, 6, 9. Can you spot the core trend here? Your examiner is testing your ability to recognize a linear sequence. Now we move to step 4, generalizing the triangle pattern. We need to link our variables t for total triangles and h for horizontal lines. Sam often rushes this part and gets the variables backwards, writing h in terms of t. Always read the command word. If it says find a formula for t in terms of h, t must be the subject of your equation. Let's do challenge 2, find the flaw. I'm going to show you how a student might lay this out. If h is 0, t is 3. H is 1, t is 6. H is 2, t is 9. If Sam wrote that adding a third line makes t equal 15, what's the flaw? The flaw is inconsistent addition. Our table clearly shows a constant difference of positive 3. Every time h goes up by 1, t goes up by 3. We are essentially adding another layer that contains exactly 3 new triangles. You must prove this constant difference to the examiner to secure your evidence marks. Now for challenge 3, speed writing. You have 30 seconds to write one perfect PL paragraph explaining the formula. The correct formula is t equals 3 times the quantity of h plus 1. Why h plus 1? Because even with 0 horizontal lines drawn inside, you still have that original 1 base layer of triangles. So you take your horizontal lines, you add 1 for the base layer, and you multiply the whole thing by 3. This is how you explain your reasoning. You don't just drop the formula, you link it back to the physical geometry of the shape. But what happens when the exam throws a variation at you? Let's take that same big triangle, but this time draw 2 vertical lines from the top apex down to the base. If you count them up with 0 horizontal lines, you now have a baseline of 6 triangles.
If you draw one horizontal line across them, that immediately doubles to 12. The underlying rule is shifting. This is the exact moment Alex panics because the formula he memorized no longer works. But you won't panic because you know the system. You just adapt your baseline. Because our starting group is now 6 instead of 3, the multiplier simply changes. The new rule is T equals 6 times the quantity of H plus 1. It is that simple. The inductive reasoning process is identical. Gather the data, map the progression in a table, isolate the constant difference, and build your formula. It doesn't matter if it's painted cubes or bisected triangles, the hacking strategy remains exactly the same.
Finally, let's look at Step 5, visualizing vector mathematics. This is another area in the 0580 syllabus where students completely misunderstand the core concept and lose basic marks. Let's compare pure algebraic addition to visual representation. On the left, we have algebraic vector addition. You take vector -3, 5 and add it to vector 4, 1. Alex just does the rote math. Top row, -3 plus 4 is 1. Bottom row, 5 plus 1 is 6. The answer is the column vector 1, 6. Fine, he gets a point. But when the examiner asks him to describe the transformation, he's lost. On the right, we see the visual representation. A vector is not just a fraction without a line. It is an instruction to move. It's a translation. On a grid, -3, 5 means start at a point, move left 3 spaces on the x-axis, and up 5 spaces on the y-axis. Adding the second vector means from that exact landing spot, you move right 4 spaces and up 1 space. Your final destination perfectly lands at a relative coordinate of +1, +6. You have to understand that the software plotting these movements is visually proving what the algebra tells us mathematically. When you grasp this, questions about vector paths and geometry become incredibly intuitive. So, there is your complete Cambridge Mathematics answering system. We took painted cubes and turned them into polynomials. We sliced up triangles to uncover linear equations, and we translated vectors across a grid. The 3 rules that guarantee top marks are: 1. Command word decoding. Know what investigate actually means. 2. The Peel framework application. Point, evidence, explanation, link. Never just write a formula without the working. And 3. The time management matrix. Don't be like Alex drawing 1,000 cubes. Use induction to jump to the answer. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @aceexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Keep investigating, and I will see you in the next session.